this opportunity. Today I'd like to talk about the minimal model program for projective morphisms of fitting complex analytic spaces. Okay? Let's start the introduction. Let us start with some simple example. Okay? First example is minimal resolution of singularity. Let y be a projective algebraic variety defined over C. In this case, we can always take a projective resolution. This is a projective resolution. This means I is a projective bidirectional morphism and X is a smooth variety. We can always take a projective resolution by Hironaka. And then by BCHN, Birkar, Cascini, Hacon, McKernan, we can run the minimal model program over Y. So we can construct the following commutative diagram, X to Y. This is a projective resolution, and this is a finite sequence of flips, and this is a contraction. So this is BCHN, and finally get relative minimal model by C. And we can see this map is a partial resolution of singularity is of Y with some good property. Okay?
So you're running the K-axiomatry over Y?
Yeah,
Okay.
Yeah, a standard minimal model program. Property. Okay, the simplest case is Y is a normal surface with only isolated singularity. In that case, this is a resolution and contracting minus curve in fiber. Then we get the minimal resolution of singularities. And it's very important for the study of singularity of Y. And for higher dimension case, even when X is smooth, that may be singular. But that has only mild singularity, so we can see this map is a partial resolution of singularities of Y. And for the study of singularities of Y, this map plays a very important role in general. So let's recall Brown's theorem. Let's pick Y here. A germ of projective healthy. Healthy means Karnavalov terminal singularity. Then the local fundamental group I1 Y regular part T is finite. Okay? Sorry, I know nothing about fundamental groups, so please do not ask the detail. But anyway, we need BCHN. In the proof of this theorem, he used this kind of argument. By using minimal model program, he constructed a good partial resolution and apply something and get this result. So here we need BCHN. So we need this assumption, Kaji projectivity. Okay. So my motivation is I would like to establish a minimal model program for projective morphism of complex analytic spaces. So if we can apply the minimal model program for complex analytic spaces, then we can use this argument in the complex analytic setting. Then we can remove this condition. So his result holds for germ of complex analytic germ of LT singularities. Okay? This is one of my motivation. So I would like to discuss minimal model program for complex analytic spaces. Okay? In the second example, this is related to Krikov model. Let by x to y here projective morphism of complex analytic spaces. And in this example, y is a disk. Y is a one-dimensional disk. Okay. Okay. And we further assume pi is semi-stable. So this is a semi-stable degeneration of projective manifolds. Okay. In this session, we want to run the minimal model program NP over y. Okay. Yeah. So if we can apply the minimal model program, then we can construct the following commutative diagram. This is the projective morphism, semi-stable morphism. And if we can apply the minimal model program, then we get a new model. And if the canonical divisor of the general fiber is trivial, in that case, after finite many flips and divisorial contraction, the canonical divisor of total space is we can make the canonical divisor of total space is trivial. So it's a higher dimensional analogy of Krikov model. But unfortunately, we cannot directly use BCHM because Y is only a complex analytic space. So I would like to establish minimal model program for complex analytic spaces. So once we obtain a minimal model program for complex analytic spaces, we can directly remove quasi-projectivity from many results. Okay.
I don't know if for Brown result, maybe some algebraic approximation of your not quasi-projective KLT singularity would be enough to determine the finiteness of the fundamental group.
Sorry, I don't know. Sorry, I know nothing about the Brown theorem.
But what I'm saying, I mean, this is cut maybe by some holomorphic equation, and then you truncate that, and you take bigger and bigger truncation. I don't know if we know that the fundamental group stabilize, because in that case, probably is enough to check it for a quasi-projective.
Sorry, yeah. Anyway, yeah. So sorry, I'm not familiar with that. Yeah. Okay, yeah. Anyway, this is my one of my motivation. Okay, and let's go to today's main theorem. This is a very rough version. BCHM works for projective morphisms. Of complex analytic spaces. Okay. So as I explained, we can remove quasi-projectivity from that theorem, and we can construct higher dimensional Kirchhoff model, and so on. Okay, this is today's main theory. But yeah, from now I would like to explain this in detail. Okay. Okay. Section. Main result. Okay. I think the most difficult problem is to find the correct setting in order to discuss minimal model program for complex analytic space. So most difficult problem is to find the reasonable setting. Okay. Setting. Okay. First one is this one. Let X to Y be your projective morphism of complex analytic spaces. Projectivity is in this example because I would like to discuss minimal model program. Okay, and this is by definition. There is this pi amp line bundle on X. Okay. And in general, X and Y are not compact. So we need some finiteness assumption. So second condition, this is very important. W is a Stein compact subset of Y, such that the ring of homomorphic functions on W is Noetherian. Okay. And, we call this condition P. Okay. So more precise version of the theorem is as follows. In theorem, let pi x to y and w satisfies P. Okay. This is a projective morphism between complex analytic spaces, and W is a Stein compact subset. I will explain Stein compact and this condition later. W satisfies this condition. W is a compact subset, and which is Stein compact, and satisfies this condition, finiteness condition. Ring of holomorphic functions on W is Noetherian. Under this assumption, a complex analytic version of BCHN, Birkar, Cascini, McKernan holds for I x to y around W. Okay? This means if necessary, we have to shrink y around W. Around W means in each step we shrink the y around W. Okay? Okay. And, more precisely, pi x to y and W satisfies P. P, and the pair x delta is KLT, Fermat-Log terminal pair. We can define KLT singularities for complex analytic space in the complex analytic setting, and delta is phi big. Big distribution to general phi by phi is P. And we further assume x is q factorial over w. Okay, this condition is very subtle, but it is not important in this talk, so I skipped the detail of q factoriality. But we assume x is q factorial over w, and C is an effective divisor such that that pair, this new pair, delta plus C, is still KLT, and kx plus delta plus C is pi net over W. Okay. Then we can run the minimal model program with scaling. Minimal model program with scaling. Scaling of C over Y around W. Around W. Okay. BCH proved this theorem for projective morphism between projective varieties, and W is empty. Okay. So they proved in this situation we can have a minimal model program with scaling. For complex analytic setting, we fix this time compact subset which satisfies this condition, and the minimal model program with scaling it holds around W. Around W means in each step we shrink Y around W. Okay, so we have the following. Yeah, we have the following.
Is the end product of the MMP still cofactorial?
Sorry?
Is the end product of the MMP still cofactorial?
Sorry, the minimal model program?
Yeah, you run the minimal model program and you get to the minimal model. Over W, the minimal model is still cofactorial.
Yeah, of course, yeah.
So for the semi-stable degeneration setting, W would just be the point, over which the central fiber lives.
Yeah. If Y is a disk, so we can take W a smaller disk, a smaller compact disk, or of course we can if W is a point, then it's okay, always okay.
Can you explain the role of C in the theorem? Can you explain the role of the scaling C in the theorem? Why do you put it in? I mean, maybe it's a naive question, I'm sorry. Like C. Why? C. Yeah, why is it here?
The C is technically important, but for application, C is not so important. Please ignore. Okay. In order to prove the termination, C plays very important role, but for geometric application, C is not important. So running the minimal model program.
Is this condition necessary condition for this time compact subset?
Necessary means what do you mean?
Like without assuming this, do you have a counterexample to the MMP?
Yeah, I don't know the counter example, but this is a sufficient condition. Yeah. Okay. And so we have a finite sequence of Lipps and divisorial contraction, Lipps and divisorial contraction. as in algebraic case, contractions over y. Starting from x delta, this is x delta 0, and out of the finally we get xm delta m. Okay, and each step is free for divisorial contraction, and the final model xm delta m is a minimal model. Model of x delta over y, or has a modified basket structure over y. But as I explained before, in each step, if necessary, we shrink y around w. So this means this is a minimal model of delta over some open neighborhood of w. Okay? And this means after shrinking y suitably, xm delta m has a modified basket structure. Okay? So this is a complex analytic version of minimal model program with scaling. And as an obvious corollary of this theorem, of course, these results are obtained by BCHM when x to y is algebraic. And I, x to y, and w satisfy P. Okay. And we assume delta is pi big, and x plus delta is pi to pseudo effective. Okay. This means numerically this is the limit of effective divisor, or this one, or kx plus delta is pi big. Okay. Under this assumption, first statement is x delta has a minimal model over some open neighborhood of W. Okay. So this theorem says after finite many flips and divisorial contraction, we can construct a minimal model. Okay. But in each step you have to shrink y. So x delta has a minimal model only over some open neighborhood of W. Okay. Second one, if kx plus delta is pi big, in this case, x delta has a log canonical model. Of x delta over some open neighborhood of W. Okay? So one says after finite many flips and divisorial contraction, we can make kx plus delta is nef and big over W, and by using the base point free theorem, we can construct bilateral contraction and get a mechanical model. Okay, and the final one is if kx plus delta is Q Cartier, then the relative log canonical ring. This is by definition M push forward Ox M kx plus delta is locally finitely generated graded over algorithm. This means for any given point P of y, we can take open neighborhood of P, and on that open set, this is a finitely generated OY algebra. Okay? In our case, Y is a complex analytic space, and Y is not necessarily compact. So we need infinitely many covers. So the statement is only locally finitely generated graded over algebra. Okay. So yeah. Anyway, these complex analytic version of BCHM, and we can use this theorem for the study of singularities where concept free-form model and so on.
Sorry, this is also you need like some open taking open neighborhood, or it's unnecessary.
Open.
Sorry, is it necessary to take open neighborhood Y to say like a locally finite generated, or you can say this for original X over Y, or you need to shrink Y.
No. Yeah. In order to prove this theorem, give any point, and yeah, some suitable W, and apply this theorem.
I see.
Yeah. Okay.
You can take W as a point. No?
Sorry?
You can take W equal to the point.
Yes. Okay.
So then this also alpha doesn't require shrinking Y, is because you can take a canonical model, so you can group. That's what you are doing.
Yeah.
I see.
So I'd like to explain this condition from now. Okay. Let's explain property P. Yeah, P mainly P2. Okay, first I make a small remark. Stein spaces. Complex analytic space X is Stein space. This is equivalent to. This is a useful characterization by using homology Xf equals 0 for any coherent sieve F and for any positive integer I. Okay? This is any coherent sieve on F. Okay? So X is Stein. It is a complex analytic analog of affine space. And let's go to the definition of Stein compact subset. Stein compact subset. Okay? A compact subset W of a complex analytic space, it is called Stein compact. Okay. If it has it admits it's a fundamental system of a system of Stein open neighborhood. This is a definition of Stein compact subset. And we can find many Stein compact subsets. For example, X is Stein space, and K is a compact subset of A, and K hat. This is a holomorphically convex hull of K. This is by definition set of A and Fj, Fa is bounded by support Fj. Okay. For any. Okay. Since X is Stein space, so there are many holomorphic functions. And yeah, so K tilde, so X is Stein, K is obviously contained K hat, and this is compact subset of A. And we can easily say K hat is Stein compact subset. Okay, so we can construct many Stein compact subsets. And the next theorem is one of the key results in my work, Hughes theorem. X is a complex analytic space, and W is Stein compact. So subset of W, subset of X, and in this case, the ring of holomorphic functions on W is Noetherian. In general, it is not Noetherian, or Noetherian. If and only if, condition star, W intersection Z has only finitely many connected components. For any analytic subset Z, which is defined over some open neighborhoods of W. Okay? So Hughes theorem says this is Noetherian if and only some topological is equivalent to some topological condition. Okay, W intersection Z, Z is the analytic subset defined over some open network W. This is Noetherian if and only this has only finitely many connected components. Okay, this condition plays important role in the minimal model program for projective morphism of complex analytic spaces. Okay.
there a simple example of a Stein compact set for which this fails? This Noetherianness fails?
Yeah, simplest example is, for example, any offset is Stein. Yeah, and this is a compact subset. Yeah. So, yeah. So this is a bad example. Okay. Okay, we define such example. So for example, W is a Stein compact, compact subset, and we first assume W is semi-analytic. Then W always satisfies this one. Okay. In that case, W intersection Z is semi-analytic, and compact semi-analytic set has only finitely many connected components. So we can construct many Stein compact subsets which satisfy star. So for geometric application, why is this one? And in order to construct something over a smaller open subset, so we take W suitably, which satisfies this condition. It's not difficult. Why is the Stein? So, for example, embed some higher dimensional polydisk and take Oka-Beyu domain and take suitably, we can construct a semi-analytic Stein compact subset. So it satisfies that condition, and think of harmonic function and W Noetherian. Yeah. Okay. So from now, I would like to explain how to use this condition star. Okay. I explain how to use this condition. Okay. This is mainly due to Nakayama. First, let us define cycle space. W. This is a free abelian group. Generated by projective integral curve. Curve C on X such that pi C is a point of W. Okay? This is a very big free abelian group, and in this case we can consider the following intersection pairing in such U Z1 is B, and U is open neighborhood of W. Okay, so the element of this peak is a line band defined over some of the neighborhood of W. So we can consider intersection pairing. The element of this is generated by a projective curve, which maps into W, so we can define the intersection pairing. Okay, and as usual, as in the other case, we put this is the quotient by numerical equivalence plus over W. Okay, by this intersection pairing, we can define numerical equivalence class. So L equals W, L prime is found only L dot C for any Z1 or any C Z1. Okay, and we put A1 x over yw is a direct limit of this variable. Okay. And U runs through all the open neighborhood of W. Okay, so this is a variable. Theorem, which is due to Nakayama, novel Nakayama. Okay. If W satisfies star, okay, in this theorem, W is not necessarily star compact. We only assume W satisfies condition star. So this is W intersect only finitely many connected components. For any Z, Z is analytic subset which is defined over some of the W. Okay. W satisfies star, then A1 x over y W is a finitely generated variable. Okay, this is a very important result. So W is time compact, and W Y is Metarian. So this implies star, and this implies A1 x over y W is finitely generated variable. Okay. This is Nakayama. And this is due to Shu. Okay. And then we put N1 x over y W equal A1 x over y W tensor. And we can define a dual space N1 x over y W. Okay, and this is a finite dimensional vector space, and so dual space is also finite dimensional, and we can define Riemann monotone. Okay, Riemann monotone. Okay, so this is the Riemann monotone. Yeah. By Nakayama's theorem, this is finite dimensional, so we can define Kramer-Morricone as in the ideal case. And we can prove Priman's ampleness criterion. This criterion for pi x to 1. Okay. So A is pi ample over W if and only A is positive on this cone. Okay. Minus 0. Yeah, and so on. Okay, and we can establish the cone and contraction theorem and the contraction theorem. For pi x to y and w are satisfying P. This means Kramer-Morricone. Yeah. It is like this. So the x delta is K key for simplicity. Yeah. N either x over y w. This is a non-negative card plus some. Negative part is found by extremal rays, and for each extremal rays we can construct a contraction morphism, and so okay. Essentially the same statement for projective morphism of complex space.
But you're saying that once you have this notoriety and the finite generated abelian group there, all the proof, the classical proof of MMP goes through with no change?
It's suitable change. Yeah. Suitable. Yeah, suitable. Yeah. So, yeah.
This cone theorem and contraction theorem doesn't require like shrinking.
Yeah, but for contraction theorem, we have to shrink.
Oh, you have to shrink.
Yeah, and W. Yeah.
Oh.
Okay. So maybe the same question is where is the difference from the classical case and these are setting for running the minimum of the program?
Okay. Main difference. Yeah. Main difference and some difficulty is so for pi x to y and w as above, okay, satisfy P, and L is a line bundle on X or R line bundle. Okay, so in this case, L is pi ample over W. Okay, this is by definition. Okay, L restriction to pi inverse W is ample for any W. Okay, so the fiber is projective variety. So this is ample line bundle in the usual sense. Okay, ample over W means is by definition restriction fiber is ample, and we can easily say this is L is pi ample over some open neighborhood of W. Okay, if this holds, then it is obvious. And ampleness is an open condition, so the restriction is to fiber is ample. Then this is ample over some open neighborhood of small w. So this is equivalent. But L is finite over W. Okay, this is by definition. L restriction to minus W is net for any W. Okay? But unfortunately, this is not equivalent to L is finite over some open neighborhood of W. Okay? If this is finite over some open neighborhood of W, then the restriction is obviously net. But net is not an open condition, so L is finite over W does not mean L is not finite over some open neighborhood of W. This is a technically difficult point. Yeah. So for example, x delta and kx plus delta. We done the minimal model program. Then after finite many free and the contraction kx plus delta becomes finite over W. But we want to prove kx plus delta is finite over some open neighborhood of W. Okay? The definition of a minimal model, we require this condition. Net over some open neighborhood of W. But running the minimal model program, we can make kx plus delta only finite over W. So this is a big difference. So there is a conjecture x delta is a KLT pair, and phi x to y are projective. Of course, this is these are complex analytic space, projective morphism, and kx plus delta restricted to pi inverse p. P is a point of y is net implies kx plus delta is net over some open neighborhood of p. Yeah, this is a conjecture, and I don't know how to prove this theorem, this conjecture. But fortunately, in the case of BCHM, we always assume delta is p. In that case, we can prove this conjecture. Nef over some restriction to some fiber is net implies nef over some open neighborhood. Yeah. In our case, delta is big, so we can apply base point free theorem and so on. So we can prove this conjecture. So we can imitate the proof of BCHM, and we can translate almost everything into complex analytic setting. And So for final remark, BCHN, remark, BCHN only uses Hironakazu resolution of similarity is and Kawamata-Fielding vanishing theorem はまたreject vanishing theorem. So, and we have already known Hironaka's resolution holds for complex analytic setting with some suitable modifications. So, this point is, so we can use Hironaka's resolution in our setting, and the Kawamata-Fielding vanishing theorem can be generalized for projective morphism of complex analytic spaces. This is because we can use analytic method, Elit's method, for Kawamata-log terminal pair. So we can prove Kodaira vanishing theorem and Kawamata-Fielding vanishing theorem for complex analytic projective morphism of complex analytic spaces. So we can use these techniques in our setting. So we can imitate. We can translate the arguments of BCHM into complex analytic setting. But as I explained, there are subtle problems. Pi F over W does not imply L is pi F over some of the neighborhood of W. So there are many technical difficulties in each step. So in some step we have to prove L is pi F over some of the neighborhood of W, or restriction to some sufficient general fibers pi F and so on. So yeah, so we have to take care of this difference. But anyway, essentially the same proof of BCHM works in the complex analytic setting. Once we assume condition B, the finiteness condition. Okay, I stop here. Yeah, thank you very much.